Annenberg Media.
Imaginary, having existence only in the imagination, unreal. Now, my English teacher always told me it wasn't really correct to use a word in its own definition. So let's take a look at imagination. Imagination, the ability to deal creatively with reality. To meet the challenges of survival on this planet, human beings have come up with some pretty creative solutions. Imagination has also been a key ingredient in the development of mathematics. Measuring the success of the hunt by making scratches on a piece of bone, the first form of counting, was a wildly creative concept in its own time. Now, counting posed no conceptual problems as long as you could see the things being counted, the number of fingers on both hands, say, or the number of members of a particular tribe. But what happens when you want to count the number of bison in a herd or stars in the night sky? Even now, perched at the end of the 20th century, our minds are still overwhelmed when trying to comprehend the number of stars in our universe. The enormousness of the task transforms our desire to count the uncountable into an exercise in philosophy. And if we look at the actual exercise of counting, it should dazzle us even more, if you can imagine that. We can grasp that there must be a limited number of stars in the universe, even if we can't count them. But how about numbers themselves? Are there any limits to them? Well, no. Here's the symbol that we use to describe such endless situations. It stands for infinity. We've all grown fairly accustomed to using the word without too much thought about what it really stands for. We ran into the concept while talking about number lines. The early Greeks gave us the idea in the mathematical form ... Now, calculations involving infinity are a bit too esoteric for this series, but there are some other concepts we deal with which also caused quite a stir when they were first introduced. For instance, zero and negative numbers. What do these mathematical ideas actually mean? Though you and I accept zero and negative numbers with little hesitation, the lack of natural world counterparts made them quite extraordinary in early mathematical history. But by using such unnatural numbers, their inventors were able to represent previously difficult real-life situations and communicate them effectively to other mathematical converts. As superintendent of the Athenian Sculpture Guild, you could now easily check your records to see if you were out of stone from amalgamated marble. And your account could tell you how much those foot-dragging Trojan dealers were overdrawn on their deposit for Hellenic figurines. Doing the impossible was, of course, not confined to the science of mathematics. From Italian inventors in the 15th century to backyard mechanics in turn-of-the-century America, powered flight remained an elusive goal. Finally, just the right balance of power, weight, and wing design was achieved by the Wright brothers, and the sky literally became the limit to flight. But before mathematical thought could try out its wings, an obstacle had to be overcome. That obstacle, the square root of -1. And the only way mathematicians could break through that barrier was to use their imagination to create a new kind of number. Only 100 years after Leonardo da Vinci's flying machines, a new type of number was hypothesized. These odd new numbers took nearly as long as powered flight to become part of our reality. Not really surprising when given the less than reassuring label of imaginary. Curiously enough, imaginary numbers are essential in the modern engineering of wing design. Imaginary numbers are one of the key mathematical ideas to be explored in this program. We'll also learn about complex numbers. They're unique in the world of numbers because each is a real number paired with an imaginary number. We'll come to understand why mathematics needs complex numbers. We'll learn to add, subtract, multiply, and divide complex numbers. We'll see how to do something that we thought was impossible when we learn to factor the sum of two squares using the set of complex numbers. And we'll see how to envision the complex plane and learn how to use it to graphically locate a complex number. So how did these new imaginary numbers come to light? Well, a hypothetical mathematical situation posed by Jerome Cardan, an Italian mathematician, physician, gambler, and philosopher in 1545, demanded mathematical recognition of their existence. So what exactly are these imaginary numbers, and why do we need them? Well, let's stop talking about them and go find one. First, look at this seemingly harmless equation. Remember that the square root sign indicates that some number multiplied by itself equals the number under the sign. In a flash, you say to yourself, there's no square root of a negative number. And if I rewrite the equation using an exponent, the problem is even more apparent. A negative number squared is positive, and a positive number squared is also positive. No real number multiplied by itself is negative. So what kind of number could x be if we're going to solve this equation? Some imaginative thinking is needed here, and it doesn't seem reasonable to throw away all the rules we've learned for real numbers. More imagination is required when we talk about situations that are hard to picture in the world of real things. Getting people to accept the idea of zero and negative numbers was quite a feat, but maybe this time mathematicians had gone too far. But wait a minute. This is just the type of challenge that imagination was made for. Mathematicians tackled it head-on by doing what amounts to saying there is a solution to the equation x equals the square root of negative 1, and the result is unlike any other number. All right, if we accept that, how can we show this new number? To avoid confusion with real numbers, we've got to give this new number its own unique symbol. We could call it Z1, or asterisk 1, or just plain asterisk. We could give it any label we fancy. But as it turns out, a mathematician by the name of Leonhard Euler beat us to the punch by about 250 years. This is the symbol used to identify our new type of number. And after all, what could be more suitable than I for imaginary numbers? The square root of negative 1 is an imaginary number. In the language of algebra, we can state this: I equals the square root of negative 1. Or I squared equals negative 1. And it follows that I cubed equals I times I squared, which equals negative I, since I squared is equal to negative 1. I to the fourth is I squared times I squared, which is the same as negative 1 times negative 1, which equals positive 1. You can continue to raise the power of I, but the result will always be one of these four values. Now, it would only be natural to ask how we can apply rules that we established for real numbers, say in regard to exponents, to imaginary numbers. Well, in this program, we'll examine the relationship between the set of real numbers and the set of imaginary numbers, and the rules that they obey. I tells us we're working with imaginary numbers, but any real number times I is an imaginary number. These are all imaginary numbers. Let's take a look back at our number line. Remember this line? It represents all the real numbers, including the subsets of natural, whole, integers, rational, and irrational numbers. Now, where would you put imaginary numbers? Here's a clue. It's another line, but how is it different from the line for real numbers? As you can see, it's perpendicular to the other line, and we'll make it intersect the real number line at 0. Now we have a number line for all imaginary numbers, both in the positive and the negative directions. Interestingly enough, this graphical approach to looking at imaginary numbers originated in the mind of Danish surveyor Caspar Wessel in 1797. His work was overlooked for years because he didn't have traditional mathematical credentials, just a lot of good mathematical imagination. It was nearly a century before professional mathematicians recognized the true genius of the surveyor's work. Now let's look back at our two axes. For clarity, I've labeled a few unit markings. Again, The horizontal line represents real numbers, and the vertical line represents imaginary numbers. But notice what else I've done with these two lines. I've created a plane. Well, if my two axes create a plane, then exactly what mathematically is all this space? What happens if we step off the lines? I'll follow the real axis out to, say, 2, and then go up parallel to the imaginary axis to the point opposite, let's say 3i. The point I'm describing is here. This point is located on the plane created by the real and imaginary number lines. There are no other points on the plane exactly like it. To talk about a point, we give its coordinates in the plane. The coordinates for this number are 2 and 3i. Now let's change the way we view these numbers. Looking at the coordinates as an algebraic expression, we have 2 plus 3i. This is our first glimpse of a complex number. A what? A complex number. Looking at 2 plus 3i, we can create a rule that can be used to express every complex number. A complex number consists of a real number plus a real number times I. Symbolically, we can write any complex number as a plus bi, where a and b are real numbers. This expression, a plus bi, is called the standard form of a complex number. But suppose we let b equal 0. Then this expression would become the single real number a. And indeed, all real numbers can be described by the expression a plus 0i. On the other hand, if the real number a equals 0, then the complex number a plus bi reduces to the imaginary number bi. So it follows that the set of real numbers and the set of imaginary numbers are both subsets of the set of complex numbers. Mathematician Benoit Mandelbrot, building on the work of mathematicians before him, decided to take on what he felt to be the tyranny of Euclidean geometry. Euclid's geometric world, populated by squares, circles, cones, spheres, and other very regular shapes, didn't seem very applicable to the irregular forms found in nature. Mountains are not cones, Mandelbrot would say, nor islands circles. These pictures are visual representations of some of his work with fractals, the name he gave to the highly irregular geometric shapes used to build the forms seen here. Mandelbrot's work with fractals came directly out of his work with complex numbers and the plotting of those numbers in the complex plane. Mandelbrot had worked for many years with real numbers, but his results only hinted at the richness of the information contained in his calculations. Only seasoned mathematicians could get a sense of what he was seeing. But suddenly, in a stroke of intuition, he introduced complex numbers into his calculations. And like taking a painting, which we've seen only from the side, and which looks like a line, he turned the picture face on to us. We've been marveling in the sheer beauty of the results ever since. All these pictures are magnified sections of a set of complex numbers called the Mandelbrot set. Here's how the Mandelbrot set is graphically represented in the complex plane. Work with the Mandelbrot set and related fractal imagery continues to expand our insight into the shapes and forms of our world. They're used to analyze subjects as diverse as the pattern of air passages in the lungs and models for predicting earthquakes. In the interest of learning to walk before learning to fly, let's first perform some basic operations with these new numbers. Let's go back to the standard form for complex numbers, the real number a plus the imaginary number bi. I want to add two complex numbers, so first I'll create another complex number, c plus di. The arithmetic with complex numbers looks similar to that involved in the addition of two binomials, but remember, I is not a variable as x is in the standard rules for polynomial operations. We know I as a constant value because every time it's squared, the result is -1. With this distinction in mind, here's the definition for addition with complex numbers. Substituting some complex numbers into this expression, we can see the process in a more natural setting. Remember to keep close track of the signs. Next, there's the expression defining subtraction with complex numbers. The complex number a plus bi minus the complex number c plus di equals the quantity a minus c plus the quantity b minus d times I. Let's insert some real number values for the variables a, b, c, and d. The complex number 12 plus 5i minus the complex number 8 plus 3i equals 12 minus 8 plus 5i minus 3i, which equals 4 plus 2i. There's also an expression showing the definition for multiplication with complex numbers, but we don't really have to worry about memorizing this one. Though I cautioned you against thinking of complex numbers as binomials, the FOIL method used for multiplying binomials works just fine when multiplying two complex numbers. The complex number a plus bi times the complex number c plus di equals ac plus adi plus bci plus bdi squared. The I squared equals -1, and the two middle terms have I as a common factor. So I get AC plus the quantity AD plus BC times I minus BD, which in turn equals the quantity AC minus BD plus the quantity AD plus BC times I. Substituting two complex numbers into this algebraic expression, we can again see the FOIL method of multiplication in action. Let's multiply another pair of complex numbers. This time, instead of the FOIL method, we'll use the standard definition form for multiplication. This example illustrates a shortcut we can apply when the two complex numbers we wish to multiply are identical except for the sign on the imaginary part. Such complex numbers are called complex conjugates. When multiplying complex conjugates, the coefficient of I always becomes 0 and thus eliminates I from the result. So all you need to do is square the real number and add it to the square of the real number coefficient of I. Here's the formal way for stating this rule. As the result a squared plus b squared indicates, the product of a complex number and its conjugate is always a real number. If I turn the standard complex conjugate form around like this, I get, which may look a bit familiar. Yes, we have just factored the sum of two squares, something we learned we couldn't do when we were learning how to factor polynomials. Now, there certainly would be a problem if we weren't careful about stating the number sets to which our rules pertain. The rule for factoring the sum of two squares applies only to complex numbers. And remember, it comes from learning how to multiply complex conjugates. Are real numbers a subset of any other set of numbers? Yes. Which one? Complex numbers. What other set of numbers is a subset of complex numbers? Imaginary numbers. What is another way of writing this number? 3 times the square root of -1. 3i. What is the product of 6i times I squared? -6i. Is I a constant or a variable? A constant. Now, let's get back to complex conjugates. Is this property of any other use in working with complex numbers? Yes. Complex conjugates are also the key to doing division with complex numbers. Since complex conjugates always result in real numbers when multiplied together, they're a great tool for simplifying division problems expressed as fractions. So, to do division with complex numbers, first multiply the numerator and the denominator by the complex conjugate of the denominator, and then simplify the result. Remember that I has the real number coefficient of 1. Okay, we've learned to take a few steps in this imaginary realm, but let's see if these new numbers can actually help us fly. Wings are common to almost all methods of flying, both machine and animal. To understand how wings permit flight, let's take a crash course, better make that a short course, in physics. Here we have a diagram of moving air. The arrows indicate the direction of flow. Now, I'll put an object into this airflow and see what happens. Imagine this is the cross-section of a cylinder. We can see that the air must move around the object in order to maintain the flow. Could such a static cylindrical shape work as a wing? No. In the Earth's atmosphere and gravitational field, This hypothetical wing couldn't provide the necessary lift. Without lift, the prevailing force in this picture is gravity, which as forces go is fairly single-minded in its effects. Knowing that lift must exceed gravity if flight is going to be achieved, the shape of the wing cross-section must be redesigned. By changing the wing, we also change the airflow around the wing. The way in which air flows over the wing is directly related to the amount of lift the wing provides. As it turns out, this is a fairly typical form for a wing cross-section. So how does it provide lift? Wings lift as a result of differences in air pressure. Basically, the fast-moving air above the wing, having to go a further distance than the air under the wing, creates a pressure imbalance. The air crossing the top of the wing is at a lower pressure relative to the air moving below the wing. The higher pressure air, in an effort to fill the lower pressure void, pushes the wing up. Voila, lift. But how are complex numbers involved in the design of new wings? Now, I'm not an engineer, as I'm sure this project is bound to prove. So I'll turn things over to someone a little more knowledgeable in this area.
One of the tools we use in aircraft design and in wing design is a wind tunnel, which is where I am right now. What we have then is the tunnel with the air moving behind me. We have a wing suspended in the middle. The wing is actually a 3D shape, but if you take a cross-section of it, what you get is this two-dimensional shape right here, which is called an airfoil. One of the things we may want to look at is exactly how the air is moving around the wing. That tells us a lot about what kind of forces are being exerted on the wing. But it's difficult to see the air. You can't just look at it. So one of the things we use as a tool is smoke for visualization. Smoke wand experiments like this are a very valuable tool for checking exactly what's going on around an airfoil, sort of a reality check on the problem to make sure that the wing you think you designed is actually doing what you wanted it to. So for airfoil design, I could, if I wanted, build 100 different models that were somewhat close to what I thought I wanted, test them all, do the smoke tests, measure the forces, and see what I got. But that would be very expensive. It costs money to run the tunnel. It costs money and a lot of time to make the models. So that's one problem with just designing by a wind tunnel. The other problem is the issue of scale. You might think that to design a 747 wing, I could just take the wing and scale it down and stick it in the tunnel and run it at the right speed. Turns out, due to the physics of the problems, you just can't do that. It doesn't work. So what's the answer? What do we do? Well, it turns out that the best thing to do these days with our modern techniques is to use a computer. And one of the computer techniques that we can use involves complex numbers. If we take the complex number a plus bi and we call it z, and then we make a formula out of that and square it and say z squared, or the quantity a plus bi squared, we get a plot that looks something like this. What we're looking at are just a few of the lines that are represented by the formula z squared. What we're really seeing is an example of the enormous power of using a formula made up of complex numbers. In this very simple formula, z squared, where z is the complex number a plus bi, is contained all of the information to generate an infinite number of lines in between each of these lines on the screen. If I were to plot the comparable formula, z squared, where z was a real number instead of a complex number, what I would have was a single line instead of this whole plane full of information. If I use this pad to block off the right-hand side of the screen, what I get is something that looks very much like what you'd have if you put a wall in the middle of the wind tunnel and then use the smoke probe to get some streamlines. Well, we've looked at z squared. What happens if we make another formula using z? Say we look at something like z plus 1 over z. Again, z still equals a plus bi. What we get in this case is something that doesn't look a whole lot like an airfoil, but at least it's a solid body. It's a circle with the streamlines around it. Now, if we then take this and use a mathematical process called conformal mapping, we take the circle, we pull it and we stretch it, we pull all the streamlines and stretch them too in just the right way. We get something that looks like this. What we see is something that you probably recognize by now. It's our wing from the wind tunnel.
Even though this is a very simplified vision of what goes into airfoil design, it is the starting point for some very sophisticated aerodynamic studies. Complex numbers are an invaluable part of that design work. Just as number lines are limitless, so too is the complex plane. It stretches from mathematical horizon to mathematical horizon. Work with complex numbers is used at the very horizons of our own understandings, from research in the subatomic to the astronomic. But remember, these are, after all, imaginary numbers. We can't assume they'll fit all of our rules for real numbers. When we began working with radicals, we excluded negative values from the rule, the square root of AB equals the square root of A times the square root of B. Substitute -4 for A and -9 for B, and you can see the problem we'd have if we didn't make this exclusion. One expression equals 6, while the other equals -6, so the two expressions are not equal. Now, thanks to imaginary numbers, we can deal with this problem. When applying the standard rules for radicals, just simplify the roots of negative numbers by rewriting them as positive roots with an I coefficient. The standard form for this rule is the square root of -A equals I times the square root of A. So we've seen that imaginary numbers are anything but imaginary in their usefulness. The square root of -1 is just as much a number as any other. We call it I. And with the introduction of I, we've seen the creation of an entirely new number line. With the aid of a few mathematical visionaries, we've seen the imaginary number line intersect with the real number line to form a vast new plane of numbers called complex numbers. We've seen how to describe complex numbers by referring to their real and imaginary coordinates. We've learned how to do operations with complex numbers, including the handy properties of complex conjugates. So what was once viewed askance as unreal and imaginary now takes on a visionary quality. The eye of imagination is just as welcome in algebra as in any other field of discovery. You know, I should be able to put this thing together.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.